might have heard about this image taken last year of a supermassive black hole. What you might not have known is that this image required a global effort. Over 200 researchers, 5 petabytes of data, and half a ton of hard drives. While the fuss for one image, well, to understand that, we have to look through the lens of the diffraction limit. A telescope is a great way at viewing faraway objects with great detail. However, that level of detail is limited. This is called the angular resolution of the telescope. But why does this limit exist? Well, this is due to the nature of light itself. We've known for a long time now that light behaves like a wave and therefore can diffract, spread, and change directions when entering a telescope. This diffraction limits the level of detail that can be seen by that telescope. We can identify the limiting resolution by dividing the wavelength of the observed light by the aperture of the optical system. In order to increase angular resolution, we can decrease the wavelength or increase the aperture of the telescope. Let's go back to this image of the black hole. It's 50 million light years away, and while it's a huge black hole, the distance means it looks very small in our skies. In order to resolve this image, a resolution on the scale of micro-arc seconds is needed. That's equivalent to trying to resolve a piece of fruit on the surface of the moon. Plugging this into our equation gives us a telescope the size of the Earth. But we don't have a telescope the size of the Earth, so how did we get this image? Well, turns out there's a way to simulate a giant telescope with many smaller telescopes. This is called very long baseline interferometry. In order to perform VLBI, many pairs of telescopes observe the same target at the same time. Light arrives from the target and is detected by the telescopes. However, since one scope is slightly closer than the other, there is a very slight delay. This can be corrected. Notice that when the light comes from this direction, the telescopes measure an in-phase signal, which means that the peaks and the pits of the waves align. This also occurs at this angle and this angle as well. Thus, the output is something like this, which is the fringe pattern. Combining this data with the other pairs of telescopes separated at different distances allows us to virtually recreate a telescope the size of the Earth, allowing for resolution high enough for this image. But what if we want to see things even smaller than that? Well, if we want to simulate even bigger telescopes with interferometry, we can use space-based telescopes. However, if we want to look at things even smaller than that, we can use the sun to help. Since gravity bends light, by using the sun as a lens, we could create a telescope the size of the solar system. Such a telescope would let us see planets from other solar systems with amazing detail, but this technology remains far in the future. For now, I think it's safe to say that astronomy can only get more exciting.